It's too complicated. All right. So I changed my plans slightly from last class, which you probably saw when I made the classroom posting. So like if you did not do the reading that I decided to post for today, that's okay. Not the end of the world. Today's class will probably make more sense if you have already done the reading, but we're going to be on the same topic still next class. So even if like almost everybody finds this topic rough on the first day anyway, so it's not that much different than it would have been anyway. The topic that we're going to talk about both today and next time is called electromagnetic induction. And it is sort of like the reverse process of what we've been talking about in the last few classes, where we've been seeing how electricity can create magnetic fields. And the reverse is also true, that if you do certain things with a magnetic field, you can create electricity. That's what induction is about. There are two specific principles involved called Faraday's law and Lenz's law, which I have mentioned here in the little box. I'm going to give sort of an overview of them, and we'll do a lot of examples together today that are focused in particular on the Lenz's law part. Faraday's law basically says something's going to happen, and then Lenz's law is where you figure out like which direction the current is going to flow based on what's happening, and Lenz's law is the hard part, conceptually speaking. I'm going to show a few like demos, and I have a simulation, and I'm going to be putting my right hand in front of slides on my desk again to try to get you thinking about this idea. But like I said, next class will also be on the same idea because it takes time, basically. So I think I want to start. For you guys, I think I'm going to start with one of the demos. Don't worry about that diagram yet. This device here is just a little voltmeter. It's an analog voltmeter. You can see that there's a needle there. And I have the voltmeter connected to one of those solenoid coils that I was using the other day. Notice there is no battery. It's just the coil and the meter. I'm going to raise the camera up a little bit so you can see more stuff. But if I take this bar magnet and I shove the magnet into the coil, you can see that the needle on the meter jumped. So the magnet is still in there, and right now the needle's not doing anything. Boy, it like doesn't really show up, does it? It's a little better. The magnet is still in there and there's nothing happening, but if I take the magnet back out, it makes the needle move again. But the needle only ever really does anything while I am making changes. So when I insert the magnet, it goes to the right. When I pull the magnet out, it goes to the left. If I turn the magnet around so that the other pole is facing in, now when I put it in, the meter goes left. And when I take it out, it goes right. So the process is dependent on like the direction that the magnetic field is pointing, because when I reverse the magnet, I also reverse the result. It also depends on like the speed at which I make the change. It's like if I bring the magnet inside very, very slowly, you don't really see much of a response in terms of voltage being generated. But if I move fast, then you can see a big change. And if I flip the coil itself around, that also reverses things. So right now it's in a way that goes left on the way in and then right on the way out. But if I just flip this over, that reverses the direction too. So there's a lot involved here about like which way things are facing, which way things are moving, etc. And it also all depends on the speed at which the process occurs. So I can show you a simulated version of the same thing. So here is a coil of wire. There's one of the light bulb on it. And the little blue dots are the electrons. And here's a bar magnet. So when I move the bar magnet in, you can see that the electrons move. If I move the magnet the whole way through, they move back to their original location. If I go fast, the electrons move fast. If I go really slow, the electrons move really slow. And anytime the electrons move, whether they're going, like down or up, that's still a current flowing. And so that potentially can light up the light bulb, assuming they're moving fast enough to make the light bulb visible. And if I reverse the poles on the magnets, get which thing I have to click for that. Split polarity. The electrons now move the opposite directions. It's probably not too surprising. One way that you can think about all of this is in terms of those magnetic forces that we've been dealing with over the last few class periods. Yeah, Ridley? Sure. Because when I move the magnet, or if I move the coil, I can drag this around also. And that has the same, that has the same effect, basically, about relative motion between them. But anytime there's a relative motion between the magnet and the wire, I'm going to be exerting magnetic forces on the electrons inside the wire, and that could cause the electrons to move, which is the same thing as an electrical current. So it's one perspective that you can take on how these effects occur. Anytime there's this relative motion, you get forces, and those forces make the currents flow. There is a secondary way of thinking about it as well, which is what these diagrams are about. So we need a new word here. This is part of why, if you have already done the reading, will be a little bit easier for you. But we have this new word called flux. In general, in English, the word flux refers to something passing through something else. And when it comes to flux for magnetic fields or electric fields, it's the same general idea. So I would recommend that you focus your attention first on the illustration here. I have a little rectangular, you could think of this as being like a sheet of paper or a loop of wire, something like that. And it has some surface area, which I've named A. I've assigned a vector to it also. The vector has to be normal to the surface itself. And the magnitude of the vector is the same as whatever area is in meters squared. So if I have my sheet of paper oriented this way, a lot of the magnetic field lines pass through it. And so there's a lot of flux going through it in that case. But if I tilt it to face this way, so that there's now this angle here, I'm not going to be catching as many magnetic field lines because it's the effective area has been reduced. And if I turn it the whole way until this vector A is perpendicular to the field, now I'm not going to catch any of the lines. They do sort of lie in it, but none of the field lines pass from one side to the other. None of them penetrate through the area. And that's basically what this idea of flux represents. It's about seeing how much field passes through a particular area of interest. The way we calculate it is by multiplying the field in the area, and then you multiply by a cosine to represent this like orientation part. So if the field is stronger, you get more flux. If the area is bigger, you get more flux. If they're oriented close to being like parallel to each other like this, you get more flux. We're not going to need to do any math with it today, but next time you'll see some math. But the symbol for flux is this capital phi. The unit is called the Weber, but I think it's easier to just think about Teslas times meters squared. And you should also note that this quantity can be positive, negative, or zero. You would get negative values if I kept rotating it so that like the A vector were anti-parallel to the B vector. Now, as long as theta is more than a right angle, you'll get negative values. These two are both positive. This one is zero. And if I spun it further, it would become negative. So the way that this idea is connected to what I was just showing you about creating electrical currents is that if I bring my coil back into view, anytime I move this magnet in or out of the coil, I'm going to be changing the amount of flux through the coil. So if you think of this square hole here, the lighting is so terrible. I'm going to put my phone on top of my thing again. Should make the flash actually face downward. That'll help. That's like not any better. Yeah, exactly. So like if you think of this little square hole in the coil as being that, how do I turn it? So the little square hole in the coil is that area A. So like when I move the magnet closer or further away, like the magnetic field of the bar magnet is not uniform. It's not straight lines like this. Go ahead. So when I move the magnet in or out, I'm changing the amount of flux that passes through here. And you saw in the demo when I had the meter in view that I only got a voltage, or I only got a current while I was moving things around. So we have to keep track of not just the flux itself, but also the way the flux is changing. If the flux is changing, if it's getting stronger or weaker or whatever, that is what leads to these electrical currents forming. Just because there is flux, that on its own doesn't do anything. If I put the magnet in here and just leave it, there is flux through the coil right now, but there's nothing on the meter because the flux isn't changing. But if I take it out, while I'm in the process of moving the magnet, I'm changing the flux in the coil, and that is what creates the signal. So that idea that it's about changes in flux is Faraday's law. Faraday's law says that within any area that you think of, we usually only care about the areas for coils of wire, but for any area that you think about, if there is a change in the magnetic flux, that induces an electric field. And the word induce basically just means causes or creates. So if the magnetic flux is changing, you're going to make an electric field. And if there is a conductor there, like a wire, when you create that electric field inside the conductor, it's going to make current flow. That's why we care about it. And the more coils you've got, the stronger the effect becomes. Because if the wire loops around like 10 times, that basically means you have 10 times as much area effectively. It's like you've got 10 loops and you have 10 areas instead of just the one. And that's why so many electrical devices have these coils in them, is because you can amplify the effects by having a lot. Now, the other part of this, like I said, is determining which way the current is going to go. And the rule that talks about that is called Lenz's law. When I create this electricity in my coil, I'm going to have a current flowing, and anytime a current flows, it creates another magnetic field. So I have like this initial magnetic field that I'm waving my bar magnet around or whatever. I have my starting field, but when it causes current to flow in the coil, there's going to be a secondary magnetic field of that flowing current. So that's induced as well. I induce a current, and the induced current has its own magnetic field, which is also induced. And so that induced magnetic field always is going to be in opposition to whatever change started the whole process in the first place. So if I have a magnetic field that points up and it's getting stronger and stronger, the induced current is going to make a field that points down to try to oppose that. If the magnetic field points up but is getting weaker, then the induced magnetic field is going to point up to try to oppose that, to try to re-strengthen the field. It's an opposition to change, basically. And working through all of the logic of that can be tricky. It takes like kind of multiple steps of reasoning each time you want to try to figure out the direction. And that's why I'm going to do a whole bunch of examples today. Several of them I'm going to just talk through myself, and then I'll do a bunch where I give you a minute or two to think about it, and then I'll talk through it afterward. The mathematical form for these rules is written down here. The EMF that you get in your loop is negative n delta phi over delta t, or d phi dt, if you like derivatives. So it's the rate of change of the flux. That's why when you move things fast, it gives you a stronger effect. The big N is how many loops you have in your coil, just like the other day. And the minus sign basically is the Lenz's law part, telling you that the EMF is opposite in direction to the flux change, or in a way that works against the flux change. So I'm going to skip that one. Let's do an example. So I have a uniform magnetic field here that's pointing out of the screen at you. It's drawn with dots. I have a square of wire, and I am pushing that wire into the field at some constant speed v. So to figure out the direction that the current is going to flow, again, it's not like there's a battery or anything, but we're going to get an induced current flowing either clockwise or counterclockwise here. And there's two different ways that you can try to figure out the direction of the current. You can think about magnetic forces on the charged particles, or you can think about the flux. I think I'm going to do the forces part first. So I'm going to choose just a random section of wire. I'm going to think about the charged particles that are in here. I want to think about positively charged particles because I want to know about conventional current. But if you'd really rather talk about electrons, you can do that. You just have to remember to reverse some stuff. But there's a bunch of nuclei in here. These nuclei have a velocity to the right. and they are moving through this magnetic field, so there's going to be a force exerted on them by the magnetic field. So the motion is like that way, field comes out of the paper. This is like the hardest one to not break my arm while I'm doing it. Velocity is that way, the field comes out of the screen, and so my thumb pointing down or towards me. So like if I think of this as a positively charged particle, the force on that particle is down, which means that the direction of the current on this segment at least is going to be down, because all of the positive particles along this edge are being pushed downward by the magnetic force. Now, the particles up here are also being pushed down, but they can't go that way. The particles along here are being pushed down, but they can't go that way. And the particles over here, if there was magnetic field here, they would be pushed down, but there's not any field over here. So like overall, if you think about all of the charged particles, this is the only part that really matters. And so the force exerted on these particles can cause the current to go the whole way around the loop. So that's just thinking about, again, like the QVB forces. But let's think about the flux. For calculating the flux, I only care about the inside of the loop, the interior. And the flux through this loop is outward. So outward. And it's also getting stronger. Because in the moment that I've got it drawn, I could just like count the dots basically. So like the flux is 12 or something at this moment, because there's 12 dots inside. But if we wait a few seconds and the loop moves further in, there's going to be more dots. So like it's going to increase to 16 or something like that. So the change in the flux, the delta phi, delta t, is positive. So what Lenz's law says is that the induced current is going to create its own magnetic field, and that magnetic field should work in opposition to this. So opposition to this would be to make like X's, or to make inward flux, to try to prevent the flux from getting stronger. So to oppose that, I need to make inward flux or inward field. That's how I would counteract the strengthening outward flux. And now that I know which way my magnetic field should point, I can figure out which direction the current needs to go. Like the current can only be clockwise or counterclockwise. I already know from the other method that it's going to be clockwise. So I'm going to do that first. But if I let my thumb, I want to know about the field created by the current. So I'm using this rule where my thumb is the current, and then the field goes around my thumb. If the current goes this way, then I make X's on the left, and I make dots on the right. But I only care about the left side because that's the inside of the loop, that's the interior. So if the current flows this way, it generates X's on the interior of the loop, and that opposes this original change in the flux in the first place. I was getting more and more dots. I want to cancel some of those dots with X's. The way I would make X's is by having a clockwise current. So the current must be clockwise. Sure. So I'm going to do a couple more of these because I know that's a lot of separate steps to get to a single answer. So here is my next one. I again have this magnetic field that points out of the page. And I have my square loop of wire. This time the wire is not moving, but the magnetic field is getting weaker. And if the magnetic field is getting weaker, that means the lines have to spread out so that they're not as dense. Strong fields have close lines, weak fields have sparse lines. So this is the initial state, this is the later state. So as far as the flux goes, the flux is outward and it is weakening. Because initially I have like 16 and then now I have only 6. It's getting weaker. So if my objective is to work in opposition to that change, I need to make more dots. I just lost a bunch of dots. I need to try to make dots to replace them. So I want to make dots or make outward flux in order to oppose that change. And if I want to make dots with my induced current, then it's going to have to go the opposite direction from before. Last time I had a clockwise current that went down on this edge, and that made X's. But if the current on this edge goes up, now my fingers on the interior, at least, are all coming out. Dots over here, X's over here. And that can sort of reinforce the weakening field. Therefore, current is counterclockwise this time. Okay, I'm going to do one more of these and then I'm going to show you a couple of additional demos. This time we are looking like edge on at the loop. Like if you imagine this compass, the contrast on the camera is so bad. But if you imagine this compass is the loop of wire, we're like looking at the edge of it here. So it's circular, but you're just seeing the edge. And it's spinning inside this magnetic field. This is the way almost all electrical generators in the entire world work, by the way. We have a magnetic field. We use something to make a coil of wire spin, like water flowing over a dam or steam moving through pipes or something. Make a loop of wire spin around and then it induces current in the wire. That's where like all of our electricity comes from. So as this turns, it's approaching this horizontal position where it would have its maximum possible flux. The way you would catch the most field lines is by flattening it out. So I know the flux is increasing at this moment, and the flux goes up. So upward flux, and it's getting stronger. Strengthening. If I want to oppose that, I'm going to have to make downward magnetic field with my current. The induced current has to make an induced magnetic field which points down. I need downward field. So I'm going to think about this part, like the top and bottom edges, because in those two spots, the current is either going to be coming up out of the page or down into the page. And what I want to do is make magnetic field that points down. So at this spot, if the magnetic field is coming out of, or sorry, if the current is coming out of the paper, then I would have this counterclockwise field that goes around the wire. And a counterclockwise circle here does go down through the middle of the loop. On its way through the loop, it's going down. That's the induced field, and it comes from an inward current. No, outward current. Dots. Comes from an outward current. And then conversely down here, if the current goes into the page, an inward current makes a clockwise magnetic field. So when that field passes through the loop, again, it's going down. So the current up here on this end has to be out towards the camera, and the current here has to be in away from the camera. And as I said before, you can also make these same conclusions by thinking about the forces, magnetic forces. So if you imagine a positively charged particle here on this end of the loop, its velocity right now is like that way, based on the way the loop is spinning. So the velocity is this way. I'm going to do this end so I don't have to break my arm. So the velocity of this particle is that way. So if I want to know about the force, start with my hand that way. The magnetic field goes up. So I'm going to have to turn my wrist kind of like this so that I can make my fingers for the field go up. And once I've done that, my thumb is pointing into the paper. So the force exerted on particles right here is into the paper, and therefore the current flows in that direction. So in any of these problems, you can always approach them either through the force stuff or the flux stuff. Occasionally, the force part gets a little bit tricky. Like I didn't do it on this one, but like you'd have to imagine that these field lines are moving in this case. They like gradually spread apart from each other. So like this field line right here, that field line has a velocity to the left, the field. But that is tricky because, gosh, like completely illegible. And my phone is too heavy for this now. That's still illegible. I'm writing really sloppy. That says V subfield. If you want to determine the direction of the magnetic force, you have to be talking about the velocity of the particle relative to the field. So like you have to pretend that the field is motionless, but in this case, the field is moving. So like the velocity of the particles would be to the right. And if you have a velocity to the right, and the field that comes out of the page, you get a force downward, which is the same counterclockwise direction. Sure. So depending on the question that you're doing, sometimes the flux reasoning is harder, sometimes the flux reasoning is easier, because you don't have to worry about like changing your reference frame or anything like that. Okay. I want to show you a couple of other applications of this. going to turn the camera. Still not a very good camera though, so I need to try to get a better one. What you're looking at here is an extremely simple pendulum that I made out of a ruler. And there is a square of aluminum foil. I just folded up a piece of foil and it's held onto the ruler with a rubber band. But it can swing back and forth, just super fascinating. And then this vise has really strong magnets attached to either side. And the vise is so that they don't fly into each other, because then you would never be able to pull them apart because they're super strong. So what I'm going to do is put the vise here so the pendulum can swing through it. And again, this is just aluminum foil. It's not like attracted to the magnet or anything. It's not stuck. But when it swings through that space, it's not touching anything. But you can see that the behavior is very different now. Without the magnet, it just swings back and forth, gradually declining. But with the magnet there, it stops almost right away. And I can even, without making contact physically, I can kind of drag or push the pendulum around. So there's some kind of a force being exerted between them, but it's not a like traditional magnetic force where things just attract and want to stick to each other. And what's going on is a bunch of these induction effects that I was just talking about. So with the magnet in place, when the pendulum gets close to the magnets, the flux through this, even though it's not a wire, the flux that's passing through this square of aluminum is changing rapidly. So that creates a whole bunch of little electrical currents. They don't have any organized way to flow since it's not a wire. But you get a whole bunch of little currents flowing around in all random directions. Those are called eddy currents. And when current flows through something, the thing heats up, uses up some of the energy that way. And so the kinetic energy of the pendulum is basically being converted into thermal energy by getting transformed into these currents first. This is an example of something called magnetic braking, where you can reduce motion, can reduce relative motion between two things if there's a magnet involved. You just need a magnet and a conductor of any kind. And you'll make a whole bunch of currents, and that dissipates a lot of the energy, and it slows things down, makes it harder for relative motion to occur. And then I have another example of the same thing. This little, it just looks like a ball bearing, but it's like a rare earth magnet, neodymium. And then I also have this giant copper pipe. Turn this a little bit. Unfortunately, you can't see the entire pipe on the camera, but it's several feet long. I guess you can kind of see almost the whole thing here. But I am just going to drop the magnet. Notice that you haven't heard it hit the floor yet. There it is.
Wow.
Now there's nothing in here, it's just a hollow pipe. Just a copper pipe. But to get it back into view. Go in there. And there it is.
Can you see the inside on?
It looks pretty cool from the inside, but I don't have a way of getting the camera up there. And I don't want everyone to like come up because we have to stay away from each other. I could try to film it later from above and I could post it. So what's going on, again, this has a pretty strong magnetic field. So as it falls down through the pipe, if you imagine like any individual slice of the pipe as being like a little piece of wire, the flux through each one of those slices is changing. And that's going to create electrical currents that flow around through the pipe. And those currents are like eating away at the energy of the falling magnet. And so instead of getting faster and faster as it falls, it reaches like a terminal velocity of just like a few centimeters per second until it gets to the end of the pipe, because then there's no more conductor. And so it's not inducing currents anymore, and then it can speed up. So that again is this like magnetic braking phenomenon. The last thing that I want to show is my meter again. This one is not very dramatic, so I'm not convinced that it's going to be visible on camera. But I have a second coil. And I'm just going to put them right next to each other. The second coil, I bet if I use the power supply, it'll work. The second coil, I'm just going to connect to a battery. It's not connected right now. And I get everything visible all at once. Pretty close. So I'm just going to make contact with the other end of the battery. And when I touch, you should be able to see that the needle on the voltmeter gets a tiny little nudge. It's not moving very much. And that's because the battery can't produce very much juice at once. But I can cause a little bit of a wiggle in the coil there, or in the meter there. And these two coils, they are not electrically connected to each other. It's like two completely separate circuits. But when I turn one of the circuits on and off, it induces current to flow in the other circuit, even without any direct connections between them. And that also is an induction effect. That's essentially the way any kind of a wireless power transmission works. So like a wireless charger for your phone or your watch, or induction stovetops also work the same way, basically. If you have a fluctuating circuit in one place, and then you have another circuit nearby, even without its own power source, you can create current in that secondary circuit. Power transformers also work in exactly the same way. Yeah, go ahead. Did he run into the shelf?
Yes.
Okay, so let's do a few more examples for trying to figure out the direction. The overall strategy, I want to review here. The overall strategy for the flux method, at least, is to think about which direction the flux points, the initial direction for the flux. Figure out whether that flux is going to be getting stronger versus weaker. Figure out to oppose that change which direction do you need to make additional magnetic field? Sometimes you have to reinforce the field if it's weakening. Sometimes you have to try to cancel it out if it's getting stronger. Figure out which way you need your magnetic field to point, and then figure out which way you need the current to go in order to make that magnetic field. So it's like this series of steps or decisions. And then the alternative, which sometimes, possibly often, is easier, is to think about magnetic forces instead. So imagine a proton in your wire. Think about the relative motion of that proton and the magnetic field lines. Figure out which direction the force on it is going to be. The current is going to go in that direction. So that makes it more like a lot of the problems that you've seen recently. So this is the first one that I want you to try to think through on your own. Similar to one of my examples. So there's this magnetic field already present. There's a circle of wire that's being pulled out. I want you to try to go through a series of steps and figure out if the current's going to be clockwise or counterclockwise. I'll give you a minute or so to think about that.
I don't know. I have no idea.
All right, I'm going to talk through this one. If I use the flux approach, I know that the flux goes into the page, because there's all these X's. But while the loop is being pulled out of the field, that flux is going to be getting weaker. So since it's getting weaker, I want to try to strengthen or reinforce it. So I need to make more X's. I need to make a field that points into the page. And my choices are basically either clockwise or counterclockwise. So like if I think about the bottom of the loop, either the current goes left at the bottom or the current goes right at the bottom. But what I want to make is X's on the inside. So between those two choices, it's going to have to be this way, because that way the field of my wire goes into the page over here and then comes out of the page on the outside. But I only really care about the inside, the interior of the loop. So got to go left on the bottom, up on that edge, on the top it has to go to the right. So that is a clockwise current in this case. If the induced current is clockwise, then the induced field makes X's, and that's going to reinforce the weakening flux. All right, here's another. It's another circular wire loop, but this time the loop is growing. So the dashed line is like the initial loop, and it's getting bigger. The area is increasing. So think through that one.
in the future, when you do like a telephone pole, you can do it.
All right, so on this one, the flux initially is into the page again. But this time the flux is going to get stronger because as the area increases, I'm going to have more and more X's inside the circle. So in order to counteract that, I would have to make dots, try to cancel some of them out. I want to make an induced field that comes out of the paper to oppose the increase in flux. So the result's going to be the opposite of last time. I want dots. So for the bottom part of the wire, that means my thumb needs to point right. That way the field is coming out. With that, it means the current the whole way around has to be counterclockwise. That's going to counteract the change. All right, a whole bunch of you have to go leave for sports now. So go ahead. The whole time? Yep. See ya. You're right next to Kim Sue still.
I think I'm gonna fix this.
All right, here's another example. This time the magnetic field points to the right instead of like in or out. This wire loop is supposed to be circular, but you're like looking at it kind of on an edge, so it looks elliptical. But it's a circular loop and it's sliding along to the right. I want you to think about this case.
Get it?
All right. So on this one is a trick question. It's the same.
No.
So because the wire loop is just sliding along like in the direction of the field, nothing is changing. They're keeping the same angle relative to each other. The strength of the field is staying the same. The area of the loop is staying the same. No matter how long we wait, like assuming the field is infinite in size, I guess. Like as the loop moves along, it's always going to be getting these same like 6 lines or whatever it is that passes through it. That's not going to change. And if the flux doesn't change, then that means there's no induced effect. So no induction occurs in this case.
You were doing. I measured my info. Nope.
Hide that so you can't see the answer through it. All right. This one. This one I split up into 2 parts because it involves a bar magnet. So first you have to remember like which way does the bar magnet field even go in the first place. But I have this bar magnet and it's being pulled away from the loop. You already saw when I was doing the examples with my coils that definitely will cause a current to flow. But what I want to know is which way. So if you think about the loop, again, it's supposed to be a circle that you're viewing like edge on. You can't really tell which edge is like closer, but if you tell me about the current like at the top, for example, the current at the top has to be either coming out or going in. So that's ultimately the answer that I want.
So what do you mean by like direction left or right, or like in or out? Or
In or out, for the current at least.
for the current, yeah. So what,
The flux is going to be either left or right.
in going to.
Yes. Yeah, go ahead. All right, I'm going to sketch the magnetic field of the bar magnet first. The way the bar magnet field works is that the lines come out of the north and then they wrap around to go into the South Pole. So field lines kind of go like this. And then again, they like wrap around to go in on the south side. But the part that we care about is what the field is doing at the location of the loop. And at the loop, the field points to the right. So like the flux through the loop is to the right. And since we're taking the magnet away, that means the field is going to get weaker. So in order to oppose that weakening flux, we need to make more field which points to the right. I want the field to point right. Therefore, if I'm thinking about the wire here at the top, like I said before, it has to either go into the page or come out of the page. And if it's coming out, then my fingertips here on the inside of the loop are pointing to the right, which is what I want. So the field at the top, or sorry, the current at the top is coming out of the page, and the current at the bottom is going in. Out of page at top of loop. Someone is there right now. Yeah. All right, here's another one. This time there's two wires. There's this long straight wire that's already carrying a current. And that current goes to the right, and it is increasing over time. But because there's a current here, there's going to be a magnetic field that already passes through the circle. So you need to think about which direction does that field point? Is the flux getting stronger or weaker? And what does that mean about the current that we're going to induce in the circular wire? So I'm going to answer part of this. I'm going to deal with the field from the wire first. But I know that current goes to the right. So that means that the field it creates in the space above it is dots coming out of the page. And the space below it, it's X's going into the page. But I don't really care about the dots because they're not where the loop is. In the area where the loop is present, I'm getting X's. So that means that the flux through the loop is inward. And since the current is increasing, that means the field strength is also increasing. And so the flux is getting stronger. So in order to fight against that strengthening flux, I have to make the opposite kind of field. So I want to make dots inside the loop or outward field. And to make dots, it's going to have to be on the bottom of the circle. It's going to have to be going to the right. So the current has to go counterclockwise. That will make dots on the inside of the loop, which will fight against the strengthening inward flux from the straight wire. Counterclockwise. This is probably the last one. This one is basically like the wireless charger or the induction stove. So there's going to be a current flowing in the bottom loop caused by this battery. That's the battery symbol, in case you've forgotten. So first you have to think about the direction of that current. And then we're interested in the moment just after the battery is connected. So like imagine we've just turned on the lower loop. What is that going to do to the upper loop? So based on the direction of the battery, the current in the lower loop has to be clockwise. If the current in the lower loop is clockwise, that means that the field created by the lower loop is going to be downward through the loop. So it's going to make a magnetic field kind of like this. So like, here, I'll do this part. The current at the bottom of the loop is going to the left. So like inside the loop, it's like into the page or down, sort of. It's in perspective. So that means I'm also making a downward flux through the top loop. And in the moment that I've just turned the system on, the flux in the top loop is changing from being nothing, because if there's no current, then there's no flux. It's changing from having no flux to this downward flux. So the induced current is going to try to make an upward flux. And to get an upward flux, the current would have to go the opposite direction from the one that made the downward flux. So the induced current has to go the other way. And then a few seconds later, once the bottom loop is like on, the flux will no longer be changing. And so the current in the top loop would disappear. So unless this is like an alternating current, that's the way it works like with chargers and stuff. It's used as an alternating current. But if you just turn it on and then leave it on, you'll get a little bit of a response in the top loop, but just at the very beginning, and then it'll die out. The only way to keep it going is if you keep messing with the current in the source loop. And that is it for today. As I said, this is a confusing topic, so if you're feeling lost, don't panic. Yep, the bell just sounded. You're all free to go.
Thank you.
You're welcome.